class we were talking about the metallic crystal with a non-directional bonding. Basically what we tried was to fill the space with equal size spheres in as close packed a manner as possible. And we got two crystalline arrangements. One is FCC, where the stacking was of close packed planes ABC, ABC, and another one hexagonal close packed structures where the stacking was AB, AB, AB. We had seen the packing efficiency of such close packed structures is 74%, probably the highest, leaving some 26% space, which we will see today. Then while talking about that, we also said there are some metals which do crystallize as body centered cubic crystals, and either they are alkali metals or transition metals. The reason could be in alkali metals the thermal entropy being very high tries to randomize the arrangement, and if our contention is correct, then at low temperatures they should become close packed structures. We saw that they do, some of them. But in transition metals there is partial covalent nature of the bond which tries to orient the bonds rather than making the stacking close packed and tends to become body centered cubic. If that is correct, this can be seen in iron. Iron starting from 0 Kelvin right up to 910 degrees centigrade remains body centered cubic. Covalency or partial covalency is playing its role. At 910 degrees centigrade, the thermal vibrations are so much that covalent nature is overcome and becomes metallic, becomes FCC, face centered cubic. Once again, thermal energy takes over, randomization, thermal entropy increases. At 1410 degrees centigrade or so, again it becomes body centered cubic. So we can see both these arguments working in iron. So today we shall try to look at the void spaces and then try to see if I have spheres of a different size, not of the same size, what happens. So yesterday we had begun to see this. The tetrahedral void is formed like this. All right. So the A atoms on the lower plane, of 3 of them form a cavity, and the B plane comes and sits on top of these. The space in between here is the tetrahedral void. Why we call it tetrahedral void is because of the shape formed when I join the centers of these spheres. These are the 3 sphere centers, the A plane, and this is the top and the B plane. They form a regular tetrahedron like this, and then the center of this tetrahedral void is the center of the cavity which I am looking for. In the last class, we saw the is tetrahedral void, and we try to work out the size of the sphere small sphere that can be fitted in, and we did work it out to a value of about 22.5% of the sphere that forms the tetrahedron. Right. Now coming back to face centered cubic crystal, I have shown one tetrahedron. There are more such tetrahedra in this unit cell itself. Where are these? This is the corner. This is the face center. That's the face center. That's the face center. Joining these, I get one tetrahedral hole here, which is actually on this body diagonal. Like this, you can find at each corner of the cube there will be a tetrahedron formed. Right? Can we write down the coordinates of these? How many such corners would be there? There are 8 corners like that. And that shall be, the another one is going to be here on this. This corner, the face center here, the face center here, and the face center at the back, they will form a tetrahedron. So each corner is forming a tetrahedron. And if you start from one origin, you will find that one of them is at 1 by 4, 1 by 4, 1 by 4. You can start, you can do that. Put this A axis, call this as the B axis, call this as the C axis. That's the one at that corner near the origin. That's on this body diagonal. Somewhere here. Then similarly you can find out this one, which will be 3 by 4th on A, 1 by 4 on B, and 1 by 4 on C. You can find out the one on this body diagonal here. That would be 3 by 4 on A, 3 by 4 on B, and 1 by 4 on C. And then the next one you can find out, which is on this body diagonal here. That shall be 1 by 4 on A, 3 by 4 on B, and 1 by 4 on C. It will be similar, other 4 on top, but the C height, instead of becoming 1 by 4, they will be 3 by 4. It will be similar to that, okay? 1 by 4, 1 by 4, 3 by 4, and so on and so forth. You can add all the 8 coordinates. But all these 8 volumes of the tetrahedra are well within the volume of the unit cell itself. Right? So, well, this is something we have worked out. Yeah. Within this same unit cell we have 8. And how many do I have? How many atoms do I have in the unit cell? Yes, please.
4, sir.
I have 4 spheres. Number of tetrahedral holes? 8. Number of spheres is equal to 4. So there, for every sphere there are 2 tetrahedral holes. Is that clear? So if I have a crystal 1 mole, let's say 1 mole of FCC copper, how many tetrahedral holes do I have in this 1 mole of FCC copper? 2 moles. That's the meaning of it. There are 2 mole tetrahedral holes are there, and if I have spheres of the right size of 0.225 r, I can put in those 2 mole of those atoms, right. Usually you will find that when we work out, such small spheres are not there. Even hydrogen is bigger than that usually. Alright, now let us look at the octahedral holes which are formed when a cavity in the middle is the C cavity in the A plane and the B cavities are adjacent ones, and I put a B plane on top, so that adjacent cavities are in the B atoms. So this is also again a C cavity in the B plane, this is also the C cavity in the A plane, right. If I slightly tilt this, I get a picture like this. In the middle, I have a square formed by 4 spheres, 1 sphere on top, 1 sphere on the bottom. That forms a octahedral hole like this, where I have 8 faces as equilateral triangles. Until this becomes like the one which I show here. Once again, the corners here are the centers of the spheres, and the center of this octahedral hole is the center of the cavity here. So this is how a solid shape is formed, and I do not have any third kind of a void in a closed packed arrangement. These are the only 2 kind of voids which I have. One, when an B atom comes and sits on the cavity of a tetrahedral hole is formed. When adjacent B atoms are sitting in the B cavities, the middle cavity, the C cavity, neither occupied in the A plane nor occupied in the B plane, it forms an octahedral hole. Since I do not have any other arrangement of these atoms in 3-dimensional space, I have only A, B and C arrangement, I have no other cavity form.
These are found in both AB, AB and ABC, ABC.
Exactly. See, what is called A and B and what is called B and C, so you are doing naming it. Nobody has named these spheres as A, B or C. B is a closed packed plane like an A, C is a closed packed plane like B. It will be similar geometry. Between any 2 closed packed planes, the geometry will be identical. I am showing between 2 only. Similarly, it will be between A and C. Similarly, it will be between B and C. Right? It will not be different. Naming A, B, C, we have done it. Right? So it is the same thing. Whether I talk about A and B, or I talk about B and C, or I talk about A and C, it will be exactly the same. No difference. Is this clear? Right. Now I shall show you this octahedral hole in the FCC unit cell, which you see here. This is a phase center on top, this is a phase center on the bottom. These are the 4 phase centers in the middle, front and back, left and right. Okay. This form a similar figure to this. They form a figure like this, right? So therefore, I get an octahedral hole. Where is the location of the octahedral hole?
Body center.
Body center, very good. That's the location of the octahedral hole. What size sphere you can fit in there? Yes, we can work it out. radius of this sphere which is forming an octahedral hole plus the small sphere which can fit inside is half the distance equal to the edge, that is from the face center to the body center, that is a by 2. What is the relationship between a and r? Under root 2 of a is equal to 4r. So we can eliminate a from here. What you will get? Two cancels with 2 and we are left with is small r is equal to 1.414 minus 1 of r. This r goes onto the right hand side, that becomes 0.414 of r. Now what you can fit in is much bigger than what you can fit in the tetrahedral hole. That was only 22.5% of the size, but this one is 41.4% of the size, right? It's a much bigger cavity, right? Where else such locations are there in the unit cell of FCC? Edge centers, very good. All the edge centers are also identical. Because this face center here, right, this corner and a face center on top and a face center on the bottom, they form a similar arrangement what is formed here.
So here we are considering FCC type only.
FCC only. FCC is also a closed spectral arrangement, ABC, ABC.
What about AB?
AB, AB is also similar thing. Octahedral holes will be there, right? This is A, this is B, there is an octahedral hole. This will be found in the unit cell, right? And their number will also be similar. You will be able to see these things when you see the models in the laboratory to count the numbers both in FCC and HCP. I am just counting in FCC. Now, so these are the edge centers, but you see that this edge center is common between 4 cells, while this body center one is within the volume of this cell, right? So, how many of these are there? Well, that's what we have worked out. Right. So this is let's have to, I think, go back onto the previous slide. Okay. So this is there in the body center and this is also there at the edge centers. They are going to be 12 edges and each edge is common between 4 cells. That makes it 3 of such volumes of the hole plus 1 in the body center, that is well within the volume of the cell, and total I have 4, and number of spheres I have is also 4. Therefore, there is 1 octahedral hole per sphere. Right. So this is the geometry in closed spec arrangement of the void spaces, and in these void spaces some small spheres which are available can go in. Sometimes they are slightly bigger than the small hole and they squeeze the neighboring electron clouds of the parent matrix, thereby increase the enthalpy of the crystal, but by being there they can increase the entropy as well, and therefore can lower the free energy of the crystal. So something can be there in these interstitial void spaces. Such thing could not have been talked of in a diamond cubic crystal. So there is a lot of space there. It's only 34% packing efficiency. But here there is packing efficiency already 74%, and we are still talking of this. Can you tell me one good reason why should we talk about that? Covalent bonding in diamond cube was sp3 bonding. Each atom had to be bonded to 4 neighbors. Each carbon atom is bonded to the 4 neighbors at tetrahedral angles, and the octet is complete. There is no tendency to form bond with anything else. When we have come to metals to the left of group 4, group 3, 2 or 1, octet is never complete even if it is shared. That is why there is a delocalized sharing. So whatever number of electrons are there are shared by all. Sometimes or part of the time one can feel that I have all the 8 electrons, but not 100% of the time. Therefore, tendency to form bonds with as many neighbors as possible continues to be there, because octet is never complete. That is why if some other atom can come and sit in the interstitial void, which is a smaller one, but can share the electron, well, it will be going towards more octet, completing the octet in the outermost orbit, towards having the 8 electrons in the outermost orbit, which is a more stable configuration for any atom, right. Therefore, there is a tendency for having more neighbors, as many as possible, in a metallic bond which is non-directional, and octet is never complete there, alright. So that is why we have talked about these void spaces and the holes in the crystalline arrangements of metals which are close packed structures. Right, in this slide we have this is already we have worked out. Let's can write that. Here we can write that the small sphere that can fit in the octahedral hole is of the size 0.414 of R. Yep. Yeah, this we have worked out with the help of FCC unit cell. So as one of my friend asked me, what about the HCP where ABAB stacking is there? Now I am showing between 2 close packed planes. It could be AB, it could be BC, it could be AC, it could be BA. Right, this is one close packed plane. This is little darker ones, and these lighter ones another close packed plane on top, and let us call this A and let us call this as B, this is B and this is B. B is sitting top of A and I am forming tetrahedral holes. Tell me how many tetrahedral holes I have formed about this central sphere here. How many tetrahedral holes I have formed about this? I have formed 4. Somebody is right who says 4. One is this. Similarly, one there, third here, and the fourth one is formed with this as the on the A plane, the center, and these 4 or 3 on top like this. This is the fourth one. You can put a different color for this. maybe these are the B atoms on top and this is going towards A in the bottom. So, it is an inverted tetrahedron. While the other three were upright tetrahedron, this is an inverted tetrahedron. And that central sphere is common to all four of them. That is between A layer and B layer. In a closed packed plane or close packing of planes, behind or below A, I shall have either B or C. It will be a similar geometry there. How many spheres will or how many tetrahedral holes will be there around the same central sphere there? Again 4. So 4 and 4 shall make it 8. So around a sphere, we have 8 tetrahedral holes. This will be true about this, this will be true about that, about this, about this, about this, about this, about that, about this. All of them it will be 8. Geometries are going to be identical, right? But how many spheres form a tetrahedral hole? How many spheres form a tetrahedral hole? 4. So when you begin to count, the same tetrahedral hole will get counted about the 4 of the spheres, because 4 of them are forming it. I counted these 4 here about this sphere, but when I begin to count about this sphere, this hole will again be counted. When I begin to count about this sphere, this hole will again be counted, right? Like similarly, when I start counting about this B atom, again this will be counted. So same hole is getting counted 4 times. So actual count is 1/4 of this. Okay, so that will be actual number will be 8 divided by 4, because each one is getting counted 4 times. So that's what we get an FCC unit cell. That's what we see in between any two close packed planes, AB, BC, CA or AB, BA, whatever you want to take, it is the same thing. Is that clear? All right. So that's what we have worked out. The effective number of tetrahedral voids per sphere is only 2. Now let's look at the octahedral voids in the same manner. Again 2 layers A and B. Alright, these ones are A and these ones are B. Now the tetrahedral void, so the octahedral void formed is now here. Three spheres of A, let's put it. And 3 spheres of B, if I join them, they form an octahedral hole. Like this. An octahedral hole is formed in that manner. Now let's take one central sphere, which is this one here, let us say. This central sphere, let me cross it like this. About this I have counted one octahedral or seen one octahedral hole here. About this there is another octahedral hole here. About this another octahedral hole is here. So I have 3 octahedral holes in the A layer and the B layer. But if I continue in the 3 dimensions, behind the A layer or below the A layer, there will be either B or C. With similar geometry, I shall have 3 more tetrahedral holes there. So around this central sphere, I have 3 in this layer above and 3 in the layer below. I have 6 octahedral holes. Are you able to see this? Right. Then one hole is formed by how many spheres? 1, 2, 3 of A, 1, 2, 3 of B. So when I start counting about one sphere, 6 holes like this, same hole gets counted 6 times, right? So effective number of octahedral voids per sphere would be, we have counted 6 around 1, we have counted 6 around 1 and 1 is formed by 6, so that makes it 1. So 1 octahedral void per sphere. So if you have 1 mole of FCC copper, you have 1 mole of octahedral voids, and it can have inside 1 mole of some atoms which are smaller in size of the order of 0.414 R can go in there. Right. Now since we started talking about something going in of a different size in the interstitial void spaces, these tetrahedral voids and octahedral voids, also called the interstitial void spaces. As the word interstitial, TITI comes twice, and this is also the void space is also times called interstices. Void spaces are also called interstices. Right, or you call them whatever void spaces we talked about, tetrahedral and octahedral in closed packed structure. If it is not a closed packed structure, it need not be tetrahedral and octahedral. Okay. Right, here I show maybe a simple cubic arrangement in which these are the void spaces in which smaller spheres are sitting. These are different atom, different element, and they have gone in there and dissolved in the crystalline arrangement. It is called a solid solution. Like you have liquid solutions, we have solid solutions as well. What is the difference between a solution and a mixture?
So in mixture there is no fixed proportion.
When I mix sand and stone, you call it a mixture. Go to the market to buy some grains, you mix wheat with rice, it's a mixture. When you dissolve sugar in water, you call it a solution, or when you dissolve salt in water, you call it a solution. Can you tell me the difference?
Chemical bond.
When it is a solution, mixing occurs at the atomic or the molecular level. When it is a solution, The mixing occurs at the atomic or the molecular level. Is that clear? That's why since now it is happening at the atomic level, interstices are between the atoms, spaces between the atoms, I call it a solid solution, right? And interstitial solid solution is the one where the solute goes and sits in the interstices, the void spaces. Okay, this is the solute, and these are the solvent. Like we have seen, while trying to mix water and alcohol, you can mix them in all proportions. You can start with 100% water, keep on adding alcohol, keep on removing maybe water, ultimately you can have all alcohol. It will still be the all solution always. But if you try to do that with sugar, you cannot. You can dissolve sugar up to the limit, then you call it becomes a saturated solution, and then if you add any more sugar, it doesn't dissolve. So in one case I have a limited solubility, other case I have extensive solubility. In solid solutions, sometimes even 20% solubility we can say extensive, right? But in this case of kind of a solid solution, can you have extensive solubility? Firstly, I cannot have spheres which are of so small a size that they can go in interstices without disforming the neighboring atoms, without distorting the neighboring spheres. Therefore means there are going to be an overlap of electron clouds. When that happens, the energy, the enthalpy of the system goes up. Only if it is compensated by the entropy, it is stable, free energy is lower. Otherwise, it will not go into solution. Secondly, I can put in as many spheres as many interstices are there. Let us talk about an octahedral hole, which is a bigger one. I can probably, let us say, find out a sphere which is of the size of 0.414 R, let us say so, and that goes in there. So I can put maximum as many solute atoms as many solvent atoms are there, because there is 1:1 ratio. I have one octahedral void per sphere, so I can put 50-50. I cannot make solute more than 50%, right? So extensive solubility or going in all proportion is just not possible. In interstitial solid solutions, we always invariably get only limited solubility. Right. Then I have another kind of solid solution, wherein the solute goes and substitutes for the parent atom. Say for example, this solute or this solute. What is the difference between these two solutes? This one is bigger than the parent atoms, thereby you can see that it is compressing the electron clouds. Here the electron clouds have to extend to form the bond with it. It will depend upon which electron clouds are more flexible, whether electron clouds of the solute are more flexible or the electron clouds of the solvent are more flexible. The bonds have to be extended, bond length has gone up. Electron clouds have to extend, right? That means there is going to be an increase in enthalpy here, there is going to be an increase in enthalpy here, right? And this is compensated by the increase in entropy, configurational entropy, therefore it is there. Such solid solutions do form. and we call them substitutional solid solutions because the solute is substituting for the parent atom or the solvent. Solvent is removed and solute is placed in place of that. Say for example, I have copper and I add to it nickel. I can replace one atom of copper, put one atom of nickel, place another atom of copper, put another atom of nickel. I can go on doing this. I started with FCC crystal of copper. If I do that, I end up with FCC crystal of nickel. If nickel doesn't exist as FCC, that's not a stable configuration. It will not be possible. But if nickel stays as FCC, stable, it will be possible, right? So I can get very large, extensive, or rather solubilities in substitutional solid solutions, could be from 0% to 100%. Like the example of alcohol and water, they can mix in each other in all proportion. Gold and copper can do so, copper and nickel can do so. They can mix in each other in all proportions. But that's possible because one is substituting for the other. To get the extensive solubility, certain empirical rules found by Hume Rodri for the substitutional solid solutions. Shall look at those. Let's try to understand them one by one. These are empirical rules, and therefore please understand they are not so rigorous. I will give you the examples also after this, we will discuss them. Firstly, the extensive solubilities are possible on substitutional solid solutions only, not in interstitial solid solutions. Size difference, it says, should be within 15%. I am talking about the linear size, the diameter or the radius, not the volume. That should be within 15%. Since these are empirical rules, please do not ask 15% of the solute or 15% of the solvent. Okay? So that marginal adjustments you have to keep in mind. 15%, if the size is within that, let's say size difference is 5%, extensive solubility is possible because the strains in the electron clouds to form the bond will be very small, right, and that will be compensated by the entropy increase. That's important, very important empirical rule of the second one. It says the electronegativity difference should be small. What happens, let me ask the question, if the electronegativity difference is large? Yes, let us say one element from group 1, other one from group 7, like sodium and chlorine. Chlorine is more electronegative, it will take the electron out from sodium, which is more electropositive. And one becomes positively charged, other becomes negatively charged, there is a different kind of bond formed now, which is called an ionic bond. This is no more a metallic bond, okay, and therefore electronegativity difference should be small, otherwise they will tend to form a compound. I am looking for solid solutions only. Then I talk about the valency. Valency, please understand, is not the chemistry valency you have studied in school, chemistry, or the first year chemistry here. This valency, by that I mean, is number of electrons in the outermost orbit. Number of electrons in the outermost orbit, right, should be same. There can be still possibility with the difference of one or so that you can get extensive solubility. If it is same, there are more chances that we shall get the extensive solid solubility. Then it says crystal structure should be same. Example I already given. If in gold, which is FCC, I replace gold atoms by copper atoms, it becomes FCC copper, and it is possible to become FCC copper if copper also exists as FCC, which it does in this case. Otherwise, it will not be possible. Right. Now, with the help of example, we will talk about these. These 4 parameters: crystal structure, the atomic radius, the valency, the number of electrons in the outermost orbit, and the electronegativity. Okay. Let's take the example of gold and copper. Just now I said size difference, you can see, is within 15%, right? Valency, number of electrons in the outermost orbit, is the same. Electronegativity difference is not large, and they dissolve in each other in all proportion. That's why all the goldsmiths are able to give you impurities. They can add copper easily without much problem, right? All these carats, different carat of gold, 22 carat, 16 carat, 18 carat, less the number, more the copper is going to be there. Okay. So, alright, so that's we get complete solubility. Between copper and nickel, you see, size difference is still smaller, but valencies differ by 1, electronegativity difference is still smaller than that. They also dissolve in all proportion. Let's look at germanium and silicon. Diamond cubic, both of them, size difference is very small, valency is the same, electronegativity is same, they dissolve in each other in all proportions. But I give you an exception: silver and copper. I can dissolve 5 to 7% only, not more. That too at about 725 degrees centigrade. At lower temperatures, the solubility is less. At higher temperatures, the solubility is still less. Maximum solubility around 725 degrees centigrade. Though crystal structure is same, size difference is within 15%, valency is the same, and electronegativity difference is 0. This is an exception. That's why I said Humbro-Urey rules are only empirical rules, right? Now let's talk about an example of copper and zinc. It's an interesting example to talk about copper and zinc. One is FCC, other is HCP. Certainly I cannot have 0% to 100% solubility, right? Size difference is not very large. Similar kind of size difference as in the copper and nickel. Valency difference is same like what we have in copper and nickel, and electronegativity difference is also not large. And what we find is, it's possible for us to dissolve almost 40% zinc in copper, while I cannot dissolve more than a few percent of copper in zinc. Almost 40% zinc can go in copper. You have 70-30 brass, you have 60-40 brass, 40% zinc is there, 30% zinc is there, it goes in solution. But I cannot dissolve copper in zinc. The reason here is slightly different, and we can try to understand that. It's a possible explanation. Copper has only one atom in the outermost orbit. When we add zinc to it, which has 2 atoms in the outermost orbit, number of electrons in the outermost orbit goes beyond 1, tending to go towards 8, but never goes to 8. It's going towards 2. 40% zinc can go in. But when I add copper to zinc, it's already 2. But when I add copper, which has 1 electron in the outermost orbit, it is going down per atom. It is not tending towards 8, right? That's why you cannot dissolve too much of copper in zinc, while almost 40% zinc can go in copper. So there are exceptions to the empirical rules as well. as is the case with the silver and copper. The solid solutions which we have seen, the substitution of solid solutions, these could be random or these could be ordered. Say for example, what I talk about random solid solution, let us say nickel going in copper. Nickel replaces the copper atoms randomly. I have added, let us say 30% nickel in copper, it dissolves in all proportion, so 30% dissolves, but randomly replaces it in FCC. This is a random solid solution. In other words, if you look at any atom in the FCC unit cell, 30% of the time it is nickel and 70% of the time it is copper. Effectively, that atom is behaving as if it is 70% copper and 30% nickel. Such is a random solid solution. Ordered solid solutions, the solute has a fixed location in the unit cell and the solvent has a fixed location. Say for example, I talk of brass, which is a copper zinc alloy, both are 50-50 and they form a BCC solid solution. In this BCC solid solution, let us say on the body center is the zinc atom, and the body corners are copper atoms. And every unit cell is like that. This becomes an ordered solid solution. Okay, but this happens in this alloy which I am talking about, copper zinc alloy, 50-50, below about 450 degrees centigrade, but above 450 degrees centigrade, thermal energy or the oscillations are so vigorous, then it becomes random. That means this is 50% time copper and 50% time zinc. This is also 50% time zinc and 50% time copper. Then at that time it is random solid solution. But once it is like this, it is an ordered solid solution. Now what is the difference as far as if you take a diffraction pattern from an ordered solid solution and a random solid solution? What will be the difference in the diffraction pattern? In other words, what will you specify the space lattice or define the crystal structure as?
So in random we cannot strictly define it because we will be getting different diffraction patterns from different layers.
In random solid solution, it shall remain BCC. Each atom is behaving as a 50% copper and 50% zinc, because it is 50% time here it is zinc, 50% time it is copper.
It is in ordered.
In ordered solid solution, this is no more BCC, it is simple cubic space lattice, and my motif is going to become this. So crystal structure and diffraction pattern, I shall get that of a simple cube, not of BCC, because it's not changing its location, it is there. That's why I am calling it ordered. Is that clear? Right. So this is about the solid solutions, and we have already introduced in terms of solid solutions putting in atoms of different sizes, and that we shall continue with that in the next class when we have spheres of different sizes and we go to ionically bonded crystals. Two ions will be of spheres of different sizes. That's we shall see in the next class.